In this video, we will be learning how to calculate the pH of a strong base solution. For our first example, we have calculate the concentration of OH- and pH of a 0.0802 molar CaOH2 solution. We have a couple steps to accomplishing calculating the OH- and pH for the solution. The first step will be to write the ionization equation. Once we have the equation, we can find the molarity of OH-. And to find the molarity of OH-, we're going to be turning the moles of CaOH2 from the molarity given into moles of OH- using the mole ratio. The third step will be to find the pOH of the solution. And the last step will be to find the pH. For all strong bases, we have 100% ionization, and this means that all of the ions are going to completely split apart. So we have one full arrow to show this 100% ionization, and we'll write our two ions, Ca2+ and OH- as products. We do need the equation to be balanced. So we have 2 OH- for every 1 CaOH2. And this part will be important for the mole ratio, where we have 0.0802 moles of CH2 per every 1 liter of solution. But if we would like the concentration of OH- instead, we're going to use the 1:2 mole ratio from the equation, and we have 2 moles of OH- for every 1 mole of CaOH2. The moles of CaOH2 will cancel, and we're going to have 0.160 molar OH-. Our concentration of OH-, one of the answers that we need, will be 0.160 molar. For the pOH, we're going to take that concentration of OH- and use the equation pOH equals negative log of the concentration of OH-. And when we take the negative log of 0.160, we have a pOH of 0.795. In the concentration, there was a total of 3 significant figures, so the pOH will have 3 after the decimal. In our last step to find the pH, we're going to use 14 equals pH plus pOH, and we're going to subtract 0.795 from 14 to get a pH of 13.205. So we have two answers here, the pH and the concentration of OH-. The pH value shown of 13 is very high, and this is what would be expected for a strong base solution unless it was diluted, so the pH would decrease slightly. For our next example, we have calculate the concentration of OH- and pH of 2.36 grams of NaOH in 450 milliliters of solution. Even though we are given different units for this problem, our goal will still be the same. For a concentration of OH-, we would like to have moles of OH- on top and liters of solution on bottom. So our first step will be to find the moles of OH-. And to find the moles of OH-, we're going to take the 2.36 grams of NaOH, use the molar mass to turn it into moles of NaOH, and then use the mole ratio from the equation to find moles of OH minus. For our second step, we're then going to find the liters of solution. And this will just be a prefix conversion to turn milliliters to liters from the 450 given. And then we can take those two units and combine them to find moles of OH minus divided by liters for our molarity. Then with that concentration of OH minus, we can find the POH and then the pH. We first want to write the equation. So we have NaOH separating into Na plus and OH minus. We want to make sure that the equation is balanced and it looks good. We will have a 1-to-1 mole ratio between NaOH and OH minus. Starting with the 2.36 grams of NaOH, we will use the molar mass to convert to moles of NaOH. And then from the equation, we'll use the 1-to-1 mole ratio to convert to moles of OH minus. And after calculating, this gives us a value of 0.0590 moles of OH minus. In a separate calculation, we'll have the 450 milliliters of solution, and we'll turn this into liters of solution by using the prefix milli, and that there will be 1,000 milliliters in every 1 liter. And now we have the moles of OH minus and liters of solution separately. So we can combine those two to find the concentration of OH minus. This gives us a value of 0.131 molar OH minus. And for the POH, we can take the negative log of this concentration of OH minus to arrive to a value of 0.882 for the POH. In the pH, we can do 14 minus the POH to have a value of 13.118. We have two answers again, the concentration of OH minus and the pH for the strong base solution. In the last example, we calculate the concentration of OH minus and pH of 15 milliliters of 0.0891 molar KOH solution diluted to 300 milliliters. For a dilution, anytime we see the word diluted or we have the same compound with two different concentrations and two different volumes, we want to use the equation M1V1 equals M2V2. The first concentration and first volume will be on the left side, and the diluted concentration with the new total volume will be on the right side. So we have 15 milliliters as our first volume. The first concentration was 0.0891 molar. And we don't know what the new concentration is for the diluted solution, but we do know that the total volume will be 300 milliliters. When we divide 300 over to the other side, we get a new concentration of 0.00446 molar KOH. We're going to take that new molarity of KOH and find the molarity of OH minus instead using the mole ratio from the equation. And then we can find the POH and the pH. For the equation, we will have KOH separating into its ions, K plus and OH minus. We'll make sure the equation is balanced. Here it looks good. We're going to have a 1-to-1 mole ratio of KOH to OH minus. And we will have 1 mole of KOH on bottom and 1 mole of OH minus to convert to the concentration of OH minus. The concentration of OH minus will be 0.00446 molar OH minus. And we can take this concentration of OH minus to use in the POH equation. POH equals negative log of the concentration of OH minus to have a value of 2.351. And for the pH, we'll subtract the POH from 14 to have a value of 11.649. This example helps us to see that for a diluted concentration of strong base, we will have a pH that is going to be not closer to 7, but a little lower than the other strong base pHs that we saw for the previous examples.